speak to us on this topic and related topics of innovation, we're very, very pleased to have with us today from NASA headquarters, Dr. Prasun Desai. Dr. Desai serves as the Deputy Associate Administrator of the Space Technology Mission Directorate. In this role, he supports executive leadership, overall strategic planning and direction, and effective management for all elements of the space technology programs executed under STMD's $1.2 billion budget. Dr. Desai, welcome to Explore Mars.
I hope everyone can hear me fine. So it's my pleasure to be here. It's been a while since I've been back to campus here. I am an alma mater of George Washington University. I did my master's, right, through George Washington. So certainly great to be here and look forward to the conversation that's going to happen over the next few days. In the morning here, I'm just going to tease a few things that you will hear throughout the rest of the next activities that are going to go on today and subsequently on some of the things that we're doing. As you heard earlier in the morning just talking about that there are a lot of challenges to do a human Mars mission. We are doing a lot, but we have a lot more to do. And I'm going to give you a little flavor of some of the things that we are doing and areas that we want to go and do subsequent things that we need to get done to make a round-trip mission to Mars, human mission to Mars, possible going forward. With that, one of the things that you know that a lot of it has to do with operating with humans in destinations further and further away from what we're comfortable with. Especially on terrestrial, on being on the Earth, but we've now experiencing for a long time now with living off world, right? On the ISS. So doing operations, activities, human studies in the ISS. But that's just the first step, right? And we're trying to push further into the solar system from that perspective. And so there's, with Artemis, we're going back to the moon. And part of the aspects of going back to the moon is we're learning a lot of the things that we need as we go further into the solar system for longer journeys that will be eventually to Mars. And so there's a lot of robotic and human operations at the moon that will help prepare us for these first missions to Mars. Long duration, zero-G aspects of things, crew size, as you see in a couple of these charts here, crew size, autonomous vehicles on the surface, operating in consort with each other and coordination with the other. So there's a lot of autonomy aspects that we need to figure out how to go about doing. Whenever human civilizations have pushed forward, the thing that we need always to start off with is power, because power is limiting for what everything we need to do thereafter, right? And so there are many different capabilities that we need for power generation, right? And so the moon will be a great area for us to test out some of these aspects. More of the traditional solar power that we can do, but on the moon, 14 days you can get the solar power. The other 14 you can't. So we're looking to find more long-term aspects of power and fission surface power aspects, and I'll talk a little bit about that. And then as we go further to make these endeavors more sustainable going forward, how can we use the resources that are there to produce the consumables that we need, be it for human consumption, water or oxygen, or resources that we can use to help with the infrastructure that we want to lay down on the ground there, be it metals or other aspects, propellant obviously for doing other things. And so in situ resource utilization is another area big that we're talking about doing, and we'll talk, I'll share a couple of slides and some of the areas that we're looking to make happen. Of course, autonomy is going to go through all of this. In order to be able to operate these systems in long distances, we certainly can't do it by remote control with the time lags. Moon is not as bad, but at Mars, it's at least 10 minutes each way. And so autonomy has to be the core of how we operate all these systems going forward. So another area we're going forward with. I will leave you with a teaser with the last chart that I have, which is how you can help us identify which are the priority things that we need to work on and help the investments going forward. But some of these things that I mentioned we're working on, we're planning to do something very much in the near term, and our future planning, we will look to you to help prioritize what those things are, and I'll come back to that on my last chart. Let me start off with, as I said, we're doing a lot now. We have a lot more to go in a lot of the challenges that we have to overcome. And here are just a few items that we have done in very relatively short number of years. The video that you see here is an inflatable decelerator that we could use to land heavy payloads on Mars. Right now, we can land about 1.5 metric tons on the surface of Mars, robotic system, right, with the Perseverance and Curiosity type rovers. If we want to send humans on the surface, we've got to be able to land 20 metric tons, at least. A big difference in capability that we're looking to do. This is one potential technology that allows us to provide the drag to be able to land something that heavy, right? So this was demonstrated in partnership with ULA of an inflatable decelerated device that can be compact and packed into a shroud of a launch vehicle. And so this was a demonstration a little over a year and a half ago, off of a piggybacking off of a launch. So trying to do it in a sustainable and cost-effective manner. So we were a ride share in this lofted mission. Worked flawlessly. You can reach out on our website, Space Tech at NASA, and get more information on how that went, right? And also look at reaching out to the guys at Langley that made that happen. To the right of that is Capstone, is a small spacecraft that's in orbit right now in the halo orbit that it's going to be at the moon that Gateway is going to be in. So it's doing the navigation, timing, operations in that environment right now to help do risk reduction for Gateway as we go towards further away from low Earth orbit and geostationary orbits going there. It has worked very well. We've learned a lot from that perspective. It is doing a lot of communications activities as well while it's in that orbit. And now we're in the process of doing extended operations as it's achieved its initial success there. Moving on, the ROSA arrays. These are compact, lightweight, higher power solar arrays that we're looking to employ on various systems. This one is showing, the picture there showing astronauts replacing the solar arrays on the space station. However, they've already been deployed onto the DART mission that went to an asteroid, collided with an asteroid. They are going to power Gateway as we go further towards cislunar operations. They're also commercially available now for commercial vehicles to use that. So being used continuously in many different applications going forward. Powering that Gateway to its orbit, this rectilinear orbit around the moon, is a solar propulsion. 12.5 kilowatt highest power thrusters that we're in development right now. They're going through final testing, going very well. That's an actual real picture, unlike some of the ones that may be artist renditions. We replaced it very recently with an actual picture. That is being tested at NASA Glenn in the test chamber there. Working very well. Again, type of a propulsion system that could be one of the solutions to sending humans on a three-way journey to Mars using the type of architecture that we still are looking to define. Next to that is MOXIE on Mars. There was a ISRU experiment to be able to produce consumables on another planet, another body, in fact. Turning the carbon dioxide into oxygen on the surface of the moon. It's worked very well. It's gone through 16 cycles. The mission is, its demo is over. Being able to show initial aspects of how we can live off the land as we send humans further and further into the solar system using the local resources available. On the bottom line, just to quickly go through it, one of the aspects that we partnered in with the DARPA is to do a high advanced propulsion system of a nuclear thermal rocket called Draco. We are planning to do that demonstration in space in the next couple of years. This is one potential candidate for a Mars transportation architecture system. The agency hasn't decided on a Mars architecture system yet. We're still going through many trades, but here's one option along with the solar propulsion that you see there, as well as nuclear propulsion and chemical as possibilities. So we're doing a lot of the tech development to enable the capabilities to be ready so that once we decide how we want to go through all the different capability areas, we have the technologies in hand that can be infused into the various systems for the missions going forward. And then the last two I'll just mention, the deep space optical communication system. This is deep space communications at a higher bandwidth than typical radio frequency that we use. It is currently on the Psyche spacecraft, about 200 million kilometers from Earth here. It is working flawlessly at that distance of shooting an optical laser beam onto terminals on mountains in California. Hard to believe at that distance you can do that precision pointing to be able to do high bandwidth communications going there. So as we send astronauts potentially to a Mars mission in the future, we can provide the data that's necessary, video back and forth from that distances from there. And lastly, a lot of technologies, and here's one of them, to be able to make the landings more precise, more robust is navigation Doppler LiDAR. I put this on there is because it was on the IM Intuitive Machines first landing on the moon, testing out landing technologies where it helped to get precision velocity and position estimates as it was landing, which it was actually supposed to be only a tech demo, but it was put in line during the descent, and it worked very well and flawlessly. So here are just some of the things that we're working on now, but there's many more that we need to make this human mission as safe as possible and as sustainable as possible going to farther distances beyond geo and lunar low Earth orbit, but going to the moon and Mars from there. So we're guided by the blueprint objectives that were Moon to Mars blueprint objectives that were the agency put out last year. The objectives from there fall into four categories of science, transportation and habitation, operations, and lunar and Mars infrastructure. We in space tech I was asked to lead the lunar and Mars infrastructure aspects of it. So we're doing a lot of the technology development to enable that infrastructure on the surface from power, communications, mobility, those aspects that you need before you can do anything else. And so we're guided by the goals that are outlined. And so if you go to this document, you will see how those objectives are laid out, both for Moon and Mars, and how we plan to try to address those objectives in a phased manner. So it allows for initial operations, more sustained operations, and then long-term stays on the Moon, as well as on Mars as we go forward. And so it is a great way to get an understanding of all the things that we're looking to do on the Moon and Mars through this architecture that will be a blueprint for how we go about making investments going forward. A couple of the areas that I will talk to you about is investments that need to happen starting now so that they will be ready in the time frames that we're looking to have their use. One is continuous power on whatever body you're on. Fission surface power in particular, here is a picture, artist rendition of one on the lunar surface. We know that because of the lunar geometry, orbital dynamics, 14 days of sunlight, 14 days of darkness. And so to have continuous power, we need some other systems than solar aspects to be able to do that. We're also looking to go into permanently shadowed regions, in the south polar regions, for example, where sunlight is even harder, even in beyond that 14-day cycle back and forth. And so continuous power aspects of it. This is one technology that we have started to work to develop the capability so that it will be available for not only lunar operations, but eventually going on to Mars for the applications that will be there. And so the Moon will serve as a proving ground as we go towards those systems for Mars. shortly after this panel, I am on a flight to go to the NETS conference in Santa Fe talking about nuclear technology for space applications. And so here is a perfect example of how we're trying to leverage a lot of terrestrial capability in a more innovative way to try to do it for space applications as we go forward. Beyond the power, which we need to start off doing anything, talking about in situ resource utilization. As I said, as we go further, we want to do it in a sustainable manner that we can try to leverage resources that are local so we don't have to bring them with us. Makes the infrastructure necessary for us all to bring at a much more reduced than we have to otherwise. And so developing, creating, manufacturing in the local environment is what we're looking to do. On the moon, we certainly can try to do that through the regolith and what we believe there is water deposits in the Aitken Basin area, right? And so we're making investments, doing early missions. So on the Intuitive Machines second launch coming up, we have a prime drill that's going to characterize the lunar regolith in terms of the characterization of water concentration in there to look at if we do ISRU in terms of a water process, how would that help to be able to do that? You can produce oxygen from the lunar regolith into a different process. So we're investing in multiple avenues to figure out how we can use those resources regardless of water-wise or regolith-wise. You can also create a lot of metals from the regolith. And so the process for doing those aspects of it so that we can build and use those metals without having to bring them from Earth in terms of a logistics operations aspect of it. And so making use of that. Our strategy is to try to do some initial demos of both of those processes for in situ resource utilization, reaching to a pilot plant of trying to create, hundreds, if not a metric ton type of consumables that are going from there after these initial demonstrations. In order to do that power plant, we need a power source. And this is where the fission surface power aspect comes into it, to be able to power systems like this so that we can create the types of capabilities that are necessary for these sustained operations, be it on the moon or eventually going to Mars. So here are a couple of things. I showed you some of the things we've done, some of the things we are planning to do now, but how you can engage with us to help determine the investment priorities that we're going forward. Right now, it is open. If you go to spacetechpriorities.org, where you can go in there and help identify and rank and rate 187 shortfalls that we have defined for what we need in order to be able to go further from the low Earth orbit out into the solar system. They are not all Moon to Mars related. There are others out there too, but there's 187 that we have identified in this initial set. We would like you to go in there and rate it. It'll take about an hour, a little less than an hour, to be able to go do that. To help figure out what the community feels are the highest priority things in terms of shortfalls that we need to overcome so it can enable the types of missions that we want to do. It will be open to the end of this week, and I hope you take the advantage of this opportunity where you can be a voice in how we can make some of these capabilities come to fruition and the timing of them so that we can enable what this Moon to Mars summit is trying to do, is eventually getting to humans to Mars aspect of it, right? There is some accompanying documents with this that will give you a better description of each shortfall if you want to do that as a companion document as you're doing this ranking. So please do take the time to respond, because we think it will be very valuable to us to see what the community is thinking and be able to decide on the best course of action going forward with the investments that need to be made to enable human mission to Mars as we go forward. I will just sum up with the aspects of there are a number of other launches that are occurring using Intuitive Machines, Astrobotics, Firefly that we are going to leverage in the very near term to do some additional technology development on those flights for figuring out how to live and operate further from the solar system. And I ask you to stay tuned with those, and with this opportunity of providing feedback on the shortfalls, look to work with you all that space tech can help push some of the capabilities that are necessary to enable the human to Mars missions as we all are looking to envision to happen. With that, I'll be happy to take a question or two if there's time available, and we can go from there. Thank you. Yeah. Yes.
For the accelerator, what TRL would you say it's at right now?
I'm sorry, for the what?
To land on Mars with the inflatable heat shield, what TRL is it at now?
I would say it is roughly in the 4.5 to 5-ish type of number there. One of the nice things post that lofted demonstration is in partnership with ULA again and Langley, NASA Langley, they are looking to scale that up to a much larger descent payload capability of almost 30 to 40 metric tons type of thing for recovery of the first stage engines, the Vulcan engines on the ULA launch vehicle. And so here we are looking to make, through this process, that demonstration is leading to a commercial activity that we can use near term, but that also gets to the scale we need to be able to do at Mars, right? And so we're trying to tee up stepping stones that allow for many of these capabilities, not waiting for whenever the Mars missions to happen, but we can actually use them for terrestrial applications, and vice versa. They go back and forth to help further the Mars endeavor. So we started with trying to do something on Mars. We're helping terrestrial applications, and those terrestrial applications will help even push the capabilities to get further in the TRL from Mars. So how are we looking at that? Okay, let's go.
For efficient surface power, one of the things that was talked about in some recent MTAS studies and also in the ACR23 is that it's pretty heavy and it's a lot of weight. So how are we looking at kind of scaling that down to make it more modular to apply for surface applications?
Yeah, so that's certainly a challenge in terms of mass of the fission power system. We intend to still have it as modular as we can, but it will be delivered as an intact unit, right, from that perspective. And so we do need landing capabilities that allow for that mass allocation to be able to do that. So it is not piece parts where someone's going to bolt those pieces together. We're trying to avoid a lot of on-surface operations in that perspective, but we will be looking to try to make them as modular as we can within certain capability limits that we would have, either operationally or delivery aspects of it, right, from there. So it is not something that we would do from a Lego aspect, though.